Hello, my name is Gustavo Sutter. I'm a final year undergraduate student at Universidade de São Paulo, and this work, called An Evaluation Metric for Generative Models Using Hierarchical Clustering, was part of my undergraduate thesis done with Professor Moacir Ponte, and is still work under development. Here, a quick agenda, the topics that I'll cover. I'll give a brief introduction on generative modeling. I'll talk about dendrograms, which are key to our method. I'll talk about the proposed method itself, some experiments and their results, and also draw some conclusions. So generative models aim to estimate the real distribution that generated a set of data points. Here we have these data points represented as blue dots, and they came from this distribution represented as this green curve. However, we only have access to the points, not to the distribution, so we try to estimate a distribution that might have generated those points. Here, in this example, which is one-dimensional, it can be easier. However, when you're dealing with high-dimensional spaces, such as images, for example, it's much harder to estimate this through distribution. One very popular way to do generative modeling with images is to use generative adversarial networks, or GANs, which is a framework where you have two neural networks, a generator, which tries to create real images that look like they came from the training data, and a discriminator, which has to tell apart which images were created by the generator and which images really came from the training data. So using backpropagation, the generator learns to fool the discriminator, and the discriminator learns to get smarter not to be fooled. As we are optimizing two nets at the same time, it can be harder and can lead to some challenges. The two most common problems when training GANs is to get samples with low quality, maybe blurred, or in the worst case, only random noise, or mode collapse. Mode collapse happens when your generator fails to represent all the modes in your dataset. So here, our dataset was composed by digits from 0 to 8, and you can see on the right that our generator only generated 5s and 0s. So they have good quality, but they don't represent the true distribution, all the modes in the true distribution. So that's mode collapse. There are some metrics that were proposed to evaluate GANs and generative models in general. The two most popular ones are the inception score and the first inception distance. The inception score uses a pre-trained network on ImageNet, and it takes a fake image, it passes through the network, and it produces a class distribution for this image, and it says that this distribution must have low entropy, in the sense that it must be easily recognizable, therefore having good quality. And if you marginalize for a bunch of fake images, you must have high entropy, in the sense that they must be diverse. The other metric, first inception distance, uses the activations from the last convolutional layer instead of this class probability produced by the networks, and uses both real data and fake data. It assumes that these activations from both of these sets have normal distribution, then it estimates the parameters for this normal distribution and computes the Fréchet distance between the two normal distributions. Here, starting to talk about our method that rely heavily on dendrograms. Dendrograms are the representation of hierarchical cluster in a dataset. Mathematically, they can be seen as a function theta that maps every distance r, here in the vertical axis, to a set of clusters at that point. For example, here, theta of b gives us 3 clusters, x1 and x2, only x3 and only x4. So that's how we can represent a dendrogram using this kind of notation. And the nice thing about dendrograms is that they are equivalent to ultrametric spaces. So we can convert a dendrogram to the equivalent ultrametric spaces using the simple rule where the distance between the 2 points in this resulting space is the point in the dendrograms where they are in the same cluster. So where the branches coming through those 2 points meet. And it allows us to use some results, some things from the literature of ultrametric and metric spaces, such as the Gromov-Hausdorff distance, which allow us to compute the divergence, the distance between 2 dendrograms. However, computing this distance in an exact manner is quite expensive. Instead, we use this approximation provided by Costa in 2017, which they used to detect concept drift on data streams. Here, this formula basically says that we're going to take the greatest difference between the sorted distances. So we take all the distance, sort them, take the element-wise difference, and take the maximum here. So that's a way that we can get a score, a metric that tells us how different two dendrograms are, okay? We convert them to ultramatic spaces and use this formula. So our proposed method, called dendrogram distance, follows from the hypothesis that if the data, the real data and the fake data follow the same distribution, their clustering must be also similar. So we imagine that the dendrogram captures more about the distribution than the first and second moment. And we use a relaxation of this distance proposed by Costa using the mean instead of the maximum value, because the maximum value isn't robust to the presence of outliers. So here we use the mean. And here, basically, that's our metric. We generate a set of fake points, and with these fake points, we extract some representation, the activations from the last convolutional layers of a pretend network. We do the same thing for the real data. We create dendrograms for each of them, and then we compute the distance between the two dendrograms. Here's the formula. It's exactly the one that I showed before. However, here we have a mean instead of the maximum value. So how do we see if our metric is capturing what we want it to capture? We use sampling techniques, take a real data set, and then we sample some simulated sets, which represent a training set that the generator might have been trained on, and some generated sets. Here we have the generated set 1, which has all the modes represented here by colors, which is good. However, generated set 2 only has some of the modes from the real data, so we expect the metric to give a worse results to set 2 than to set 1. Okay. We use Sci410 for that. As I said, our representation is the last convolutional layer of a pretend network, more specifically from a inception V3. We compared our results to the inception score and to the Frechet inception distance. Here you can see on the right our results. You can see that as the number of modes gets higher, it gets closer to the number of modes in the simulated training set. Our score gets lower, which is good, because it's a distance metric. You can see that it's very smooth, and that's what we want. We want that it gradually gets better, not get better instantaneously. You can see in the middle that the Frechet inception distance also follow this pattern. However, you can see that between 5 and 8 modes, the results are basically the same there. So it doesn't differentiate a lot between those sets, those different number of modes. And you can see on the left that the inception score doesn't really get the difference in modes, and before maybe 5 or 6 modes, our results are basically the same without much difference. Another thing that we observed was how our metric performs when we are training a model, how it demonstrates a convergence of the generative model. Here we have a Sagan trained on Celeb A, and we are plotting the result of our metric during the whole training procedure. You can see here that it follows the convergence of the images. However, it has some fluctuation due to this network. This inception V3 network is trained on ImageNet, so it doesn't go well on this data set, which is composed mainly of faces. Here's some conclusions. Our metric is competitive when compared to other state-of-the-art approaches, even producing better results, as we saw on the Sci410 example. However, it's still work under development. We have things to address. First of all, we need to compare to more metrics, such as the Wasserstein distance, mode score, and kernel MMD. We also want to test on different data sets to see how robust our method is to changes in the nature of the data, and also some experiments on sample efficiency to see if we can use a set with a small number of examples and still get nice score representing that our metric is capable of detecting the presence of mode collapse and poor quality with only a small data set. So that's it. Thank you very much. I'll be happy to answer any question that you might have. Thank you. you.